In this lesson, we will be talking about monotonic functions and the first derivative test. Monotonic intervals are what we will be concentrating on. And monotonic is just a fancy math word meaning the function is increasing or decreasing on an interval. So suppose f is a continuous function on the closed interval a to b and differentiable on the open interval a to b. In the first case, if the derivative at x is greater than or 0 at each point x on the open interval ab, then f is increasing on the open interval ab. So that's really not that impressive. If you take a look over here at a graph that is increasing on some interval from a to b, so there's a, there's b. What that's saying is that if the slopes of the tangent lines are all positive, then the graph is increasing. Okay, so similarly, we can say if f prime of x, or if the slope of the tangent line is less than 0 at each point x on the interval, open interval ab, then the function is decreasing on the open interval a, b. So again, if you have a function that is decreasing, all that's telling you is that the slopes of these tangent lines will be negative. But the interesting thing here is that you can increase, like I have written over here, this graph like this, or you could increase a different way, like this. And again, all of the slopes of the tangent lines here would still be positive from a to b, so that is an increasing interval. And you could also be decreasing like this. So there's b and there's a. And again, all of the slopes of the tangent lines here would be negative. So there are a couple different ways we can look at this, and we're going to take care of these differences between this way of increasing and this way of increasing in the complete next lesson. So forget about that for now. We just want to know where functions are increasing or decreasing. So in order to find the intervals on which a function is increasing or decreasing, the first thing you're going to want to do is find the derivative, then find the critical values, which should not feel like anything new yet. This is where the work gets done. We will be doing a sign chart for this, and then we will write out the intervals based on the work we do for our sign chart. And the best way to explain how the sign chart works is to just go through an example so you can see exactly how it works. Before we get to any finding the intervals of increasing and decreasing just given a function equation, we're going to do it given a graph. So you can see here we start out with this graph and we're asked to find the intervals on which the function is increasing or decreasing and identify the relative and absolute extrema. So what we need to do here is to identify relative and absolute extrema. I think we should do that first. So throughout the entire domain of this function, the domain only goes from -5 all the way to 2, and then again from 2 to 4. So if we're trying to find any relative or absolute extrema for this graph, it would have to be an x value that is somewhere within this domain. So it looks like this is the only extrema we have. And because this is not the lowest point on the entire graph, you can see that this arrow tells you that the range goes down forever, or decreases forever, that this will be a relative minimum. So relative min at x equals 3. And I made a point not to put any y values on this graph so that you guys would understand that where a function increases or decreases is strictly a function of reporting back x values, or little domains. So let's go ahead and find out where the function is increasing or decreasing. So for the first part, again, I'm just going to work my way left to right. I mentioned it's just like finding little domains. I'm going to start over here at -5, and you can see that the graph, as you go to the right, is increasing all the way over until -1. So I'm going to start my increasing line like such, and the first part where this graph is increasing is from -5 all the way over until -1. At -1, it stops increasing and starts decreasing. In fact, it decreases forever. It just goes down forever. But the x values on which this function is decreasing for this little portion start at -1 and go down to all the way over to 2. So -1 to 2. All right, and then we have this vertical asymptote here. So that means we have to take a break. Over here, this graph was increasing until about x equals -3, but then after that point, it started increasing again. So since it was increasing, quick little stop, and increasing again, we got to keep that all as one interval. In this case over here, this graph is decreasing, and then at 2, there's a discontinuity, and then it starts decreasing again. So that discontinuity means we cannot include it as part of our decreasing interval. And if you look over here at the domain, we cannot include -2 or +2 in the domain. So that means we cannot include it as part of the decreasing interval either. So 2. And when does this graph stop decreasing? Right there at about x equals 3. Oops, there we go. And then after that, the graph starts increasing again. So when x equals 3 all the way over to x equals 4, the graph starts increasing again. All right, very good. So you may notice that for each interval I put down here, I've got a union in between them. So if there are more than one interval on which a function is increasing or decreasing, you need to join them together with a union. For these two examples, we still need to find the intervals on which the function is increasing or decreasing, but now we just have these equations, no graphs. And the goal is for you to understand what's going on without any graphs. So this goes back to those steps a couple slides ago. The first thing you want to do is find the derivative. So step 1, f prime of x. That equals 6x cubed minus 6x to the 5th power. The second step is to find the critical values. And the critical values, again, happen when the derivative is equal to 0 or where the derivative is not continuous or undefined. Since this is a polynomial, the derivative is continuous everywhere because we also get a polynomial. So that means we just have to set this equal to 0 and solve for x. So we can factor out a 6x cubed from both terms and get 1 minus x squared equals 0. And if you solve all of these factors for 0, solve them for x, after you set them equal to 0, you will get that x equals 0, x equals 1, and x equals -1. And so we have 3 critical values. And that is step 2, finding the critical values. Step 3 is to set up a sign chart. And really, that just involves using a number line. So I'm going to draw out a number line here. And I'm going to put all of the critical values underneath this line. So -1, 0, and 1. And since this is a number line, they have to be in the correct order. So -1 to the left, 0 in the middle, 1 to the right. So when we do this sign chart, so step 3 on a couple slides ago, sign chart, this is all entailed in the sign chart. Set up your number line with your critical values. Then we have to pick test values. So I'm going to do that in a different color, and I'm going to put those above the number line. So how do you know which test values to pick? Well, each critical value breaks the number line up into different parts. So I'm going to draw some dashed lines above the number line to know now I have to pick a number to the left of -1. So maybe -2. Sure. I need to pick a number between -1 and 0, so maybe -1/2. I need to pick a number between 0 and 1, so how about a +1/2? And finally, a number to the right of 1, or bigger than 1. So maybe in this case, how about 10? It can be any number, really. And so what do you do with all of these numbers? You evaluate the derivative at all of these numbers. So f prime of -2, f prime of -1/2, f prime of +1/2, and f prime of 10. Why do we pick the derivative? Why not go back to the original function? Well, if you go back to the definition of finding an interval that is increasing or decreasing, if the derivative is bigger than 0, if the derivative is less than 0, in those two statements, the red and blue statements, then we can tell whether a function is increasing or decreasing. So we evaluate the derivative at all of these test values. And so really, all you have to do is figure this out. If you put -2 in for x here and here, you're going to get back something that is positive. If you put -1/2 in for these two values, you're going to get something back that is negative. And you do that all the way across. If you put in +1/2 over here for these two, you're going to end up with something that is positive. And then again, when you come over here and put 10 in for these x values, you will definitely end up with something that is negative. And how do I notate that? And make sure I understand that this is a positive, this is a negative, and this is a positive, and this is a negative. So what does that tell you? That tells you that this is increasing, decreasing, increasing, decreasing. And you can see that these still break up the intervals. So I know now, my final answer here will be that this graph is increasing from -infinity all the way over until -1. And you want to make sure you're using the critical values here. So these numbers right here are how you will break up your intervals. So it's -infinity all the way to -1, and it's increasing again right here from 0 to 1. So I have to have my union here and get the rest of my increasing interval there. So similarly for decreasing, you can write that it is decreasing from -1 to 0, and then again from 1 all the way over to positive infinity. So -1 to 0 and 1 to infinity. And to join two intervals together, you need a union. So here, step 4, these are your answers for where a function is increasing or decreasing. So we can continue this idea for number 2. And for number 2, I'm going to reveal the steps slowly and give you a chance to find these intervals on which the function is increasing or decreasing for yourself. Hint, you will need to use the product rule. So for the second example, it was worked out very quickly. I will go over it very quickly. The first thing I want to note is that the domain is -infinity to 5, and that's because of the square root right here that limits or restricts the domain to be -infinity to 5. When you find the derivative of this, you will end up with something that looks like this. So that is the derivative of g of x, (x squared) all over 2 times the quantity 5 minus x to the 1/2 power. As you can remember, the square root and 1/2 power are the same in mathematics, plus the second part, the derivative of the second times the first, or derivative of the first times the second. So that's the second part of the product rule. And then when you set this equal to 0, the first thing you'll want to do is multiply each term by 2 times the quantity 5 minus x to the 1/2 power. That way you can get rid of the denominator. 2 times 2 will give you the 4. This to the 1/2 times this to the 1/2 gives you 5 minus x to the 1. So then you can go through and solve for x in this new equation, and you'll get set it equal to 0 and solve for x and get x equals 0 and x equals 4. So those are 2 critical values, but you also get this third critical value, x equals 5, from the discontinuity over here. If you substitute 5 in for this x, you will end up with a divide by 0. So that's step 2, finding the critical values. There are 3 of them. Step 3 over here is to put the sign chart, put the critical values in the number chart, pick some test values. So I picked -11. I figured -11 would be very easy to figure out here because 5 minus -11 or 5 plus 11, you can take the square root of 16 pretty easily. And for that same reason over here, I picked 1 because you can take the square root of 1 pretty easily here. Not 1. 5 minus 1 is 4, so you can take the square root of 4 pretty easily here. And then over here, I just picked 4.5, and I just had to work with it as best I could when I figured it out. And then I ended up getting something that was negative here, positive here, and negative here, which meant this was decreasing, increasing, and decreasing. So I can continue these lines down here. But also note that there was no need to pick a value bigger than 5 because of the domain restriction. There's no way we could have picked a number bigger than 5, because if you try to subtract a number bigger than 5 from 5, you end up with a negative number, thereby giving you imaginary numbers, because the square root of a negative number is imaginary. So then it's increasing between 0 and 4, decreasing between -infinity and 0, and again between 4 and 5. So now we get to talk about the first derivative test, and we needed to talk about the intervals on which a function is increasing or decreasing in order for us to use the first derivative test. And so right now I want to point out that the first derivative test is at the minimum good for relative extrema. We will be talking about absolute extrema at some point while using the first derivative test, but for right now I want to use, for sure we can find relative extrema without a doubt. To find the absolute extrema, you need to use a little bit of logical thinking that is outside of the first derivative test. So the first derivative test starts out, suppose c is a critical value of a continuous function f, and f is differentiable in some interval containing c, except possibly at c itself. Then we have three conclusions. The first of which is, if f prime changes from negative to positive at c, then f has a relative maximum at x equals c. And this makes sense because if you have derivatives that are negative, and then you have a critical value c right there, so that will be flat. And then all of a sudden you have derivative values that are positive. Doesn't it make sense that this point right here is a relative maximum? It tops out. And we can use this same logic to get through the second conclusion, which is, if f prime changes from positive to negative at c, then f has a relative minimum at x equals c. And again, you can draw a graph over here, or you can make your own idea. If you have something like this, and the c value is right here. That's a critical value, which means it has a horizontal tangent line there. And the slopes of the tangent lines go from being negative to being positive. Then there's a relative minimum there. Again, I think that makes a little bit of sense here. And then the following conclusion, or the third conclusion, happens if f prime has no change at c, then there is no extrema at c, at x equals c. And I should write this, there are no extrema. There are no extrema. There's no chance for an extremum at x equals c. So that's what the first derivative test tells you. Let's take a look at how this works in the context of a few examples. So in the first example, I'm going to move this here. Use the first derivative test to find all extrema and classify as absolute or relative. And so in order to do that, we first need to find the intervals on which this function right here is increasing or decreasing. Because we need to know at the critical values, is it going from decreasing to increasing, or is the derivative going from negative to positive, or is it going from positive to negative, or is there no change? So we need to know this information before we can use the first derivative test. So practicing those first few examples makes sense to help us with the first derivative test. So the derivative here is, again using the product rule, x to the 1/3 power times 1, that's first times the derivative of the second. By power rule, this is just 1, plus the second, x plus 8, times the derivative of the first. X to the 1/3 power, the derivative by the power rule is 1/3, 1 over 3x to the 2/3 power. So there's the first step. The next step is to, again, remember, we need to find out where all of the critical values are. And one of the critical values right away is at x equals 0, and that's because of this right here. That x, if you substitute 0 in for that x, you will end up with a divide by 0. So that's one of them, and that's by discontinuity. Of the derivative. The other critical values, we need to set this equal to 0 and solve for x. So 1/3 plus x plus 8 over 3x to the 2/3 power equals 0. And because I don't want to work with fractions just as much as anybody doesn't want to work with fractions, I'm going to multiply every term by 3x to the 2/3 power. And when you do that, you end up with 3x plus x plus 8 equal 0. And if you solve this equation for x, you'll end up with x equals -2. So there's one critical value. Here's another critical value. Let's get that sign chart going. So the sign chart here is the following. So I have the two critical values, the -2 and the 0, listed here and here. And I picked these values, -8, -1, and +1, because I know over here in my derivative, where I'm evaluating these numbers, I have to pick numbers that I can easily take the cube root of. So I can take the cube root of -8 and the cube root of 1 and the cube root of -1 very easily. And when I substitute -8 in for x's here in the derivative, right, f prime of -8, you end up with, or I end up with, something that's negative. So it's decreasing between -infinity and -2. Between -2 and 0, I pick -1, and when you substitute -1 in here for all these x's, you end up with something positive. So positive, that's that. And then again, we have to put one more number, evaluate the derivative at 1, and strangely, you get something that is positive again. So this graph from left to right goes from decreasing -infinity to -2 to increasing between -2 to 0, and then at 0 it stops increasing and starts increasing again. So if we were looking for intervals on which this function is increasing or decreasing, we would say that this function is decreasing from -infinity to -2, and then increasing from -2 all the way over to infinity. This is like that very first graphical example that happened a few minutes ago. But we're not interested in where this graph is increasing or decreasing. We're trying to find absolute or relative extrema. And so for this case, we can see that right here, the graph changes from being decreasing, or that the derivative is being negative, to increasing, or where the derivative is being positive. So we can say that there is a minimum at x equals -2. And the other part of that is, what is the minimum value? Well, the minimum value here is what you would get if you find f of -2. So this is where the minimum happens. This is what the minimum value is. So the minimum value ends up being 6 times the the cube root of 2. The minimum is the 6 times the cube root of 2, and it happens at x equals -2. So even more succinctly, we could say that there's a minimum at -2 comma 6 cube root of 2. But we have to classify this as being an absolute minimum or a relative minimum. And I can tell you 100% for sure that we can right off the bat call it a relative minimum. That's what the first derivative test tells us. This is definitely a relative minimum. But is there a chance it's absolute? And the answer here is yes. This is an absolute minimum. And that is because to the left of this minimum, this function is always decreasing. So no matter how far left you start, it'll be decreasing, decreasing, decreasing until you get to -2. And after that, it increases. Only ever increases. So it increases between -2 and 0, and it increases after that to the right of 0. So if you're decreasing to the left and always increasing to the right, this will end up being an absolute minimum. I'm going to move this again. There we go. So in this, we're going to do something very similar. Use the first derivative test to find all extrema and classify the extrema as relative or absolute. And again, when you're using the first derivative test, you automatically get relative. All extrema that you find are relative. We just have to use a little bit of logic to know whether or not it is an absolute extrema. So I will give you a chance to try through this one, and I will reveal the steps slowly. Okay, so here is the entire exercise. We have used the first derivative test, which requires us to find the derivative. So in this first step over here, I just went through the product rule. So the first times the derivative of the second, which requires a chain rule. So if you think of this 8 minus x squared to the 1/2 power, the 1/2 would come out to the front. That's what this 2 is doing in the denominator. And then you would have 8 minus x squared to the -1/2, which gets shoved down to the denominator. And then you have to take the derivative of what's on the inside of the square root, which would be -2x, which is what is in the numerator. And to finish up the product rule, you have the second function, which is the square root, times the derivative of the first, which is just 1. So then what I did to get from this step to this box was to reduce away the 2's and multiply this x times this x in the numerator to get -x squared in the numerator. So then the critical values are what you have to find next, and if you set the denominator equal to 0, you will see, and solve for x, you'll see that x will equal square root of 8, and x will also equal negative the square root of 8. And that brings me over here to the domain of this function. If you set what's inside the square root to be bigger than or equal to 0, so 8 minus x squared to be bigger than or equal to 0, and you solve for x, you'll get that the domain runs between negative square root of 8 and positive square root of 8. And at those endpoints, coincidentally, are where the discontinuities are, because this is in the denominator. This is the same expression as this part. So if you set this equal to 0 and solve for x, you'll get these two endpoints of the domain. Then, to find these other two critical values over here, you will need to first set this equal to 0, so -x squared over 8 minus x squared to the 1/2, plus 8 minus x squared raised to the 1/2 equals 0. And the first step would be to multiply by 8 minus x squared to the 1/2 to get that out of the denominator. And if you do that, you'll end up with an equation that looks something like this. It would be negative x squared plus 8 minus x squared equals 0. And then from there you can solve that for x and see that you'll end up with x equals plus or minus 2. I just have it separated out into positive 2 and negative 2. The third step is to find that sign chart. And this sign chart starts at negative square root of 8. The next critical value is negative 2, then positive 2, then positive square root of 8. And from here, it is not necessary to pick points outside of the domain. So you'll notice I didn't pick like negative 3 that would have been over here, or positive 3 that would have been over here, because that's not in the domain of the function. So we just have to find some values that are between negative 2 and negative square root of 8. So I just picked negative 2.1. Between negative 2 and positive 2, so I picked 0 because that's generally an easy number to work with. And I picked positive 2.1 over here. So when I evaluated the derivative at all three of these values, I got negative and positive and negative left to right, which meant it was decreasing, increasing, and decreasing from left to right. And then I found the minimum because it went from decreasing to increasing, or the derivative went from being negative to positive. So that gave me a minimum, a relative minimum at negative 2, negative 4. And at positive 2, I know there's a maximum because it goes from increasing to decreasing, or the derivative goes from being positive to being negative. So that's how I know there's a relative maximum. But then the very last part is there an absolute maximum? Is there an absolute minimum? What are these values? Well, at this point, we just have to go back to the extreme value theorem. This graph is continuous on the interval negative square root of 8 to positive square root of 8. And this graph is differentiable on the open interval negative square root of 8 to positive square root of 8. So we have found some values here that are a minimum and a maximum, and those are at the critical values. But in order to figure out whether they are the absolute max or min, we need to go through and test the endpoints. And as it turns out, if you substitute in the endpoints, the negative square root of 8 and the positive square root of 8 into the original function, you'll get, so let me write this over here. This is where the endpoints are at negative square root of 8, 0, and the positive square root of 8, 0. And we have to pick the largest and smallest y values. So the largest y value is here, which means this is in fact an absolute maximum. And here, this is the smallest y value, so this makes this an absolute minimum. So this was a little bit different. We had to use the extreme value theorem, and we could use the extreme value theorem because we had a closed interval for the original function. In this last example, this has not so much to do with using the first derivative test and much more to do with, can you understand what these characteristics are telling you, or what these conditions are telling you about a function? So I want you to draw the graph of the function that satisfies these conditions. So right away, I'm going to first of all put the extrema on this graph. So the extrema, the relative extrema at negative 4, 2, I know that's right here. Oops, I want to use blue. There we go. And at 3, -5, that is right down here. And I want to put those on there first, and I guess there's an absolute extrema at 4, 8. Huh. So way up here, 4, 8. All right. So there are those. And then I want to make sure that I get this graph right. So I know it's increasing, the graph is increasing from -infinity to -4. So these are all x values. These are not ordered pairs. Extrema deal with ordered pairs. So all these x values, let's see here. So -infinity to -4. So it is increasing. And if you go left to right, yes, this graph is increasing. So there's that. And now I want to know what happens between -4 and +3 for the x value. So -4 to 3, we can see that f is decreasing. So that's going to go something like that. And then from what? From from 3 to +4. Oh, that's right here. That's that interval. Oh, increasing again. Okay, so I'm going to connect these to be increasing as best I can. There we go. And then after 4 here on the x's, that's this interval here. It looks like it will be decreasing. So I can just do this with an arrow down. And let's double check here that these extrema are relative. So I have a relative extrema at -4, 2. Yep, this point is definitely higher than that, but it is still a maximum. The graph goes from increasing to decreasing. Cool. Let's see here. The relative extrema here, 3, -5. Yep, that's an extrema. It's a minimum. It bottoms out. But this graph continues down forever, off to the left and off to the right. So this is definitely not the lowest point. But then here at 4, 8, this is definitely the tallest point on the graph. So that will be my absolute extrema. And then it goes down forever to the left, to the right. Okay, that looks like everything is there. Now, these conditions here in orange are not necessarily given to you like that. This could also be represented as the derivative of x being bigger than 0 on these intervals. Or for this one, and that's for increasing. Remember, if the derivative is positive, then the function is increasing here and here. Or the decreasing portions, you would say f of x is less than 0 on these intervals. And again, that means if f is decreasing, or rather, let me say it like this, if the derivative, you put the primes up here, if the derivative is negative, then the function is decreasing. So you can see all the slopes of the tangent lines here would be negative, so that function is decreasing the whole time. Here, all the slopes of the tangent lines are negative, so that part of the function is decreasing as well. That concludes the lesson for the first derivative test and intervals of increasing or decreasing. The next lesson will consist of what we call concavity and the second derivative test.